So we talked about things dissolving. Now we're going to talk about kind of the opposite. So we can look at precipitation reactions and better understand what's going on by looking at the reaction quotient, Q. And Q, remember, is calculated in the same way that an equilibrium constant is. It's the same equation, but Q it can be calculated under any circumstances. K is at equilibrium only. Q is whatever we've got going on right now. So we calculate Q and compare it to KSP. If Q is less than KSP, that means the solution is unsaturated. We can dissolve more solid. So if Q is less, that means that the calcium ion concentration and or the fluoride ion concentrations are less than what they are in a saturated solution. When Q equals KSP, we're at equilibrium. The solution is saturated. And if Q is greater than KSP, the solution is supersaturated and the solid will precipitate out of solution, usually. Any questions?
This has to do with both shift to the left, shift to the right.
Mm-hmm. Stand up, sit down, fight, fight, fight. Did you have a question or that was just a comment?
That was it.
Okay.
Yeah.
Yes?
Isn't this also temperature dependent?
There is temperature dependence, but we're not talking about that right now. Yeah, because equilibrium constants are going to be dependent on temperature. So we can use Q to predict whether a precipitation will occur when two solutions are mixed. So the first thing we have to do is identify the potential precipitate and then calculate Q and compare it to KSP for that compound. So let's look at this one. A solution containing lead-2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.06 molar in lead nitrate and 0.0158 molar in sodium bromide. Does a precipitate form in the newly mixed solution? And we're told what the KSP is for PBr2. So there's two possible precipitates here. Lead with bromine or bromide and sodium with nitrate. But we should recognize that all sodium and nitrate compounds are soluble. That's not going to precipitate. So our potential precipitate is lead bromide, and we can look at how that would dissolve. Sorry, it's not lead 3, it's lead 2. Two bromides. And KSP 4.67 times 10 to the minus 6. So to calculate Q, we're going to look at the concentrations that are currently there. So the concentration of lead nitrate is 0.06 molar, and the concentration of bromide is 0.0158 molar. So Q will equal the concentration of lead times the concentration of bromide squared. One 1.5 times 10 to the minus 6. So how does Q compare to KSP? Which one's bigger? KSP is larger. the hard thing I've always found is remembering, well, Q larger than or smaller than, precipitates, doesn't precipitates. It's another one of those seemingly random pairs of things. So I prefer to just think about it instead of try to remember. So this is what Q is right now. And this equilibrium is going to proceed, this reaction will proceed until it is at equilibrium, until we get to K equals this, Q will equal that, and in order for that to happen, these concentrations need to get larger, right? So does that mean that solid is going to precipitate, or more solid is going to dissolve? How are we going to make these larger? By more of the solid dissolving, right? So a precipitate will not occur. Any questions? Nice.
It says yes.
Oh, I'm batting 1,000 today. What did I do now?
I got 1.5 times 10 to the negative fifth.
Yeah, so it is bigger.
Ah, yep. Oh, I thought I paused it and I didn't. There's going to be an awkward part in the middle of that video. Oh, well. So I've got the calculation set up correctly, and I'm looking at the screen of my calculator, and I realize that what happened is I put in 0.006. So that makes this off by a factor of 10, which in this case happens to be important. So Q is greater than KSP, and a precipitate does form. Yikes. So these concentrations give a Q that's larger than KSP. That means the reaction will go in a direction that will lower it until Q is equal to KSP. So these have to get smaller. The way they get smaller is for a precipitate to form. Which brings us to selective precipitation. Selective precipitation is when we add a reagent that will form a precipitate with one of several dissolved cations, but not the others. So we're going to precipitate one of the cations, but not the other cations. We're going to be selective about what we're precipitating. The reagent that is chosen is based on KSP values. And we'd like to have a difference in KSP values with a factor of at least 1,000 so that we can actually separate them. Because if the KSP values are too close, we'll get co-precipitation. So the concentration needed to trigger precipitation is determined by comparing KSP and Q. So a solution contains equal concentrations of barium, lead-2, and calcium ions. When potassium sulfate is added to this solution, which cation precipitates first? Question?
I was curious, why do we select cations and not anions to precipitate?
That's a good question. Why are we interested in precipitating cations and not anions? Because generally we're more interested in what cations are present than which anions are present. And I can't answer that one quickly, just because. So we need to look at the table of KSP values, which I'm having a hard time finding. Article 18.2. Pages are all stuck together. There's one, and here's two. Okay. So we need to find KSP values, and we're adding sulfate. And so our potential precipitates are barium sulfate, calcium sulfate, and lead sulfate. So since I have a textbook in front of me, I'm going to use that instead of flipping back to the screen. So iron, well, there's lead sulfate. I found that one first. 1.82 times 10 to the minus 8. Calcium sulfate, 7.1 times 10 to the minus 5. And barium sulfate, 1.07 times 10 to the minus 10. Which cation will precipitate first? It's going to be the one with the smallest KSP. So it'll be the barium sulfate. So when the barium ion concentration times the sulfate ion concentration equals this very small number, precipitate will begin to form. For calcium, that product will be a little larger. Well, somewhat, that's the highest one, and this one is a little larger. So these you can add sulfate ion, and you could get barium to precipitate without precipitating the calcium or the iron, the lead. Any questions? Yes.
Is that dependent on how much potassium sulfate you added, and then would they precipitate sequentially if you had an excess of potassium sulfate?
If you do it carefully, you can precipitate the barium as a, that's a solid then, and you can decant and separate off the solution, which then would contain calcium and lead ions. And you can add more sulfate, precipitate the lead, decant off the solution, which has the calcium ions, and then you could precipitate those.
If you threw it all in at once, would it precipitate?
Yes. If you threw in a large excess of sulfate, all three of them would precipitate. Any other questions?
I might be done. But is it 10 to the negative 10 and 10 to the negative 8 only a factor of 100 different?
Yes. Yeah, so it's not that this is going to be a good choice for separating those two completely, but the barium sulfate will precipitate before the lead does.
I know you said the temperature isn't matter right now, but if it's hotter or colder, does that affect which one of those two will precipitate?
It could, definitely. If you remember back to Chem 1A, there was a table that gave the solubility with respect to temperature. And different substances have different curves. Like the sodium chloride curve is actually a straight line, and it's almost horizontal. There's very little temperature dependence. A lot of them are more exponential going up, and there's a couple that actually are negative. The higher the temperature, the less soluble they are. Very weird. Yeah. So you could have a complete shift by changing the temperature in terms of which one was more soluble. Yeah. And this is called separation science. It's all about having these things that are mixed up and how can you separate them out. It's an important part of a lot of analysis because things get in the way, and if you can't get rid of them, then you can't look at the thing that you want to look at. So finding the minimum required reagent concentration for selective precipitation. So the magnesium and calcium ions present in a solution 0.025 molar, magnesium 0.011 molar, calcium, can be separated by selective precipitation with potassium hydroxide. What minimum hydroxide ion concentration triggers the precipitation of the magnesium ion? And we're given KSPs for both compounds. So what we're looking at here is the saturated solution at equilibrium. Anything above that would begin to cause precipitation. So which one's going to precipitate? First, it's the magnesium, right? So magnesium hydroxide and so KSP equals magnesium ion concentration times the hydroxide ion concentration squared. And I shouldn't have written that right there. So essentially what we're looking for is the molar solubility. So when magnesium hydroxide dissolves, it's going to make S amount of magnesium and 2S of hydroxide. And so KSP then is equal to S times 2S squared, which is equal to 4S cubed, and that is equal to 2.06 times 10 to the minus 13. I'm sorry, I'm off on some other problem. Yeah, just